Hey everyone. When it comes to proofs in this class for theorems, I think it's true so far. Every theorem, I've stated the theorem, and then we've gone through and worked out the proof. And that includes even some fairly complicated theorems. And that'll be the case for almost every theorem in this class. But this next theorem that we're about to cover, I'm going to state the theorem. I am not going to prove the theorem, right? This is the one case where, in the interest of time, I would like to get to other material, I'd like to cover other stuff. And so this proof is fairly lengthy, and in the end, once you've made it through the proof, I don't think that it really adds that much to your understanding of the material. So I'm going to state this one without proof. And then where our focus is going to be is in actually applying this theorem. So this theorem is called, it's got a name, so it's the fundamental theorem of finite abelian groups. Now, with a name like that, if it's got fundamental in the name of the theorem, then obviously it's important, right? So this is a key theorem in the study of finite abelian groups, and it's due to Kronecker in 1858. All right, so this goes way back, and what this is going to tell us is really going to tell us everything we need to know about finite abelian groups. So it goes like this. Let's let G be a finite abelian group. Then there exists a collection of primes, and this collection is not necessarily distinct. So there exist, we'll say, not necessarily distinct primes P1 up through, what I use here, P sub k, and natural numbers which are the case n1 through nk, 1 up through n sub k, such that G is isomorphic to Z P1 raised to the n1, cross Z sub P2 raised to the n2, cross cross Z sub Pk raised to the nk. And there's a little bit more to this, so we can say moreover, the numbers k and these powers of prime, so moreover k and the pi's raised to the ni are uniquely determined. So there's the statement of the theorem. And I should point out, so that's the end of the statement. So, but just as a remark then, this completely classifies finite abelian groups. So what is this saying then? It's saying that every finite abelian group G is isomorphic to a direct product of cyclic groups. And these cyclic groups are somehow inherent, right? They're uniquely determined by G. So what does that mean then? Anytime if two people are handed a finite abelian group and said, all right, tell me which cyclic groups which product of cyclic groups is G isomorphic to. Both people will write down exactly the same answer, except the only difference would be the order that they write these cyclic groups in. Right? Other than that, though, everyone will have exactly the same number of factors, and the primes and their corresponding powers will match. Okay, so what we want to do is understand how to apply the fundamental theorem. And so here's the idea. If someone says, I'm thinking of a finite abelian group that has order, let's say, m. According to the fundamental theorem, there will be a finite list of groups, cyclic groups, and products of cyclic groups. Let me say this better. Someone hands you a finite abelian group G. You don't need to write this part down. Then what we will do is we'll say, oh, okay, then there are only a certain number of possibilities, and your group G must be isomorphic to one of them on the list. So for every choice of order of finite abelian group, you are guaranteed there is a short list, well, I should say a short list, but a finite list of groups, and your group is isomorphic to one of them on the list. So now let's take a look at this. So let's say, suppose G is abelian with the order of G equal to m. Now, our goal then is to express G as a product, direct product, of cyclic groups. All right, so that's what we want to do. And when we say express, what we want to do is find a product of cyclic groups of the form Z sub something cross Z sub something cross blah, 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 such that G is isomorphic to that group, or to the product of those groups. So we're going to break this up into two cases. So if we're going to first do the special case. So the special case is when M is a power of 1 prime. Right? So the special case is when M is equal to P to the K for some prime P. Right? So M has exactly 1 prime factor. Now, there's one piece of terminology that we need. So if n1 dot 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 up through n sub what letter I do? N sub t are natural numbers such that n1 plus n sub 2 plus dot 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 plus n sub t is equal to k. So if we have some natural numbers that add up to k, then any one of you who are in combinatorics probably knows the answer. What's this called? So then the collection, and I want to use set brackets, but that's really not the right thing to use. So the collection n1 up through n sub t is so these are not necessarily distinct, right? We could have repeats here, right? This collection right here is, what is it? A partition of k. Now, what you want to notice then, so we'll say note that Z sub P P P raised to the n1 cross Z sub P raised to the n2 cross dot 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 cross Z sub P raised to the n sub t is an abelian group of order. So let's see now. Here, there's no group theory going on here, other than just recognizing that if you have a couple of abelian groups or some list of abelian groups, and you take the direct product, the result is abelian. So this is an abelian group, and then what is the order? Well, the order is going to be. Let's see now. How do you find the order? You multiply the subscripts. Right? Well, if you multiply the subscripts, we're going to have p to the n1 times p to the n2 times p to the n3. Add, so this is of order p to the n1 times p to the n2 dot p to the n sub t, which is equal to p. Now, when you multiply, you add the exponent, so that's p raised to the n1 plus dot plus n sub t. And that sum right there, we said, adds up to k. So what that tells us then is each time we have a new partition of our exponent k, we can cook up an abelian group of order p to the k. All right, so for each partition of k, it will correspond to a new abelian group of order p to the k. Oh, I'm sorry. Sorry. That's p to the k. Yes. And I, sorry, just got freaked out there. By the way, p to the k is equal to m, which is the order of our group. Okay, so now, according to the fundamental theorem, so according to the fundamental theorem, all abelian groups of order m, and I should highlight order m equal to p to the k, are of this form, right? So are of this form, and when I say this, I mean right there. So of this form, for some partition of k. So we need to talk a little bit more about partitions. In particular, what I'd like to do is write down the possible partitions for some small integers. So let's do this as an example. So let's fix a prime. So fix a prime p. And then I'm going to make a little table here. K partitions of k. And then possible direct products of order p to the k. So, and I just want to do this for k equal to 1, 2, 3, and 4. So when k equals 1, there's exactly one partition of 1, right? You can only just write it as 1. Which means that the only possibility, if we have m equal to p raised to the first power, if m is prime, then g must be isomorphic to z sub p. Next are partitions of 2. So if k equals 2, we can write it as 1 plus 1, or we can write 2 as 2. And so the possible groups of order p squared are going to be zp to the 1 cross zp to the 1, or z sub p squared. Now let's look at, do I have enough room? Yeah, there's only 3 of them. So for 3, we have 1 plus 1 plus 1. We have 1 plus 2, and we have 3. The corresponding groups of order p raised to the 3rd power are going to be zp cross zp cross zp. zp cross zp squared. And zp cubed. And then I want to continue this table, but I'm out of room, so I'm going to do it right over here. For 4, so if we've got 4, the partitions are 1 plus 1 plus 1 plus 1, 1 plus 1 plus 2, 1 plus 3, 2 plus 2, and 4. I think I got them all. 1, 2, 3, 4, 5. Yeah, there's 5 of them. Okay, and so then the corresponding groups of order z sub p raised to the 4th power will be zp cross zp cross zp cross zp, zp cross zp cross zp squared, zp cross zp cubed, zp squared cross zp squared, and zp to the 4th. Right? So every abelian group of order z sub p to the 4th must be isomorphic to one of the 5 groups on that list right there. And then you can continue, right? I mean, there could be p to the 5th, p to the 6th, and so on. And you can continue. It obviously gets more complicated in terms of partitions. And so let's just try one example. Sorry, I'm just checking my time here. Okay. So what I'd like to do is classify all abelian groups of order (16). Okay, well, 16 is 2 to the 4th. And so we're going to work with this one right here. We have a prime 2 raised to the 4th power. So when I say classify, here's what I want. I want a list so that every abelian group of order 16 must be isomorphic to one on that list. There's going to be exactly 5 of them. So, here's our answer, our solution. Every abelian group must be isomorphic to one of the following. And so our choices are Z2 cross Z2 cross Z2 cross Z2. Z2 cross Z2 cross Z4. Z2 cross Z8. Z4 cross Z4. And Z16. Okay? So what we have here is a list of 5 abelian groups. Every group of order 16 must be isomorphic to one of them, and none of these groups are isomorphic to each other. Right? So every abelian group, every abelian group of order 16 must be isomorphic to one of the following. Sorry. So here's our 5. There's the solution. Now, life is much, much harder when it comes to non-abelian groups, right? So abelian groups, finite abelian groups, kind of, I'm not going to say easy, right? Because it's based on partitions, but in a sense, it is quite easy, right? This completely tells us everything we need to know about finite abelian groups, right? If you give me, well, okay, I haven't generalized this yet, but if you give me a list, I can tell, if you give me an abelian group of order 16, and you say, here's a group, it's of order 16, with and it's abelian, with a little bit of work, I should be able to figure out which one of the groups on this list it's isomorphic to, right? But when we get to non-abelian groups, it's much more difficult. So let's actually try an example of that. And so here we go. Let's let H consist of the following numbers right here. So 1, 8, 12, 14, 18, 21, 27, 31, 34, 38, 44, 47, 51, 53, 57, and 64. 53, 57, and 64. So here's just this list of natural numbers. And it turns out that under the operation, right, so under the operation of multiplication, mod 65, H is an abelian group. So there's something going on here, and we'll talk about this later on, exactly why this is true. But for now, let's just accept. I wrote down this list, and you can actually show that it is a group under multiplication mod 65. Now, count them, and there's 16. Right, let's make sure I got it right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so what we have is an abelian group of order 16. According to the fundamental theorem, it must be isomorphic to one of the 5 groups on that list right there. I'm going to have to erase that right now, so take one last look at that. Our group right here must be isomorphic to one of those 5, and we're going to figure out which one it is. So the question, which group on the list is H isomorphic to? Okay, so there's our 5. And here's the way we're going to go about it, right? We want to somehow see why, or see what distinguishes these groups right here. And one thing that distinguishes them is the orders of the elements. For example, Z16 has an element of order 16. None of the other groups do. In Z2 cross Z2 cross Z2 cross Z2, every element has order 1 or 2. And so what we want to do then is write down and figure out who the orders of each of the elements in my list are, and that should help us figure out which group we've got. So let's make a little table here. So let's write it like this. So I want element and order. And I think I can fit them all here. So 1, 8, 12, 14, 18, 21, 27, 31, 34, don't run out of room, please. 34, 38, 44, 47, 51, 53, 57, 64, 57, and 64. Hopefully you can see all of this. Does this show up? Yeah, I think it all makes it in the shot. Okay, so what I'm going to do then is I'm going to figure out the order of each one of these elements. And I already did this, right? So for example, the order of 1 is the identity, is 1. And if you look at 8 squared mod 65 is not the identity. 8 cubed mod 65 is not the identity, but it turns out that 8 to the 4th mod 65 is equal to the identity. So 8 has order 4. You can check the arithmetic for each one of these. 12 squared is the identity. Oh, no. Sorry. 12 squared is not the identity. 12 squared is 144. Mod 65 is not the identity. Could the answer be order 3? Well, the order of an element has to divide the order of the group, and since we have a group of order 16, the answer is no. Right? So you're not going to see a 3 on this list at all. But 12, it turns out, has order 4. 14 has order 2. And let me just not bore you with all this. It's going to go 4, 4, 4, 4, 4. It's going to go 4 now all the way through 47. All right, so 4, 4, 4, 4, 4, 4, 4. And then 51. So then we got a 2. 2 more 4s, and then a final 2. Okay, so that's the orders of the groups. So let's see what we can do now. Z16 has an element of order 16. Since I don't see a 16 on this list, we can cross that one off the list. Z2 cross Z8 has an element of order 8. We don't see an 8 on this list, so we can cross that one off. Z2 cross Z2 cross Z2 cross Z2. This one has only elements of 1 or 2, so has only orders 1 and 2. Because there are 4s on our list here, we can cross this one out. So who are our possibilities now? It could be Z4 cross Z4, or it could be Z2 cross Z2 cross Z4. All right, so those are our possibilities now. So I'm going to just work in Z2 cross Z2 cross Z4. These elements have order 2. So what I'm going to do, remember in here we've got ordered triples, and so I want to write down some elements of order 2. How about 1, 0, 0? Right? Add that one to itself. You get 0, 0, 0. So that one has order 2. 0, 1, 0 also has order 2. 1, 1, 0. 1, 0, 2. 0, 1, 2. Wait a minute. And I think there's a couple more. But I've got 5 written down already. Z2 cross Z2 cross Z4 has at least 5 elements of order 2, and I think, 1, 1, 2 I think there's 6 of the. What did I do wrong here? I got 1, 0. Yeah. Got that one. I have 6 written down here. Which one am I missing? Oh, 0, 0, 2. So this group right here, it's probably got, I think I've got them all, but it's possible that I'm missing one. It doesn't matter. As soon as I hit, let's see, 1, 2, 3. As soon as I got right there to the 4th one, I could have stopped and said, it cannot be isomorphic to Z2 cross Z2 cross Z4. It's got to be Z4 cross Z4. All right, so by process of elimination, we're able to say, nope, can't be that one, can't be these other ones, just by thinking about the orders of the groups. And so that's how we apply the fundamental theorem, or that's how we make use of the fundamental theorem. Combined with this notion of orders of elements, we're able to narrow it down and figure out who they're isomorphic to. Okay, so let's stop there. Remember, we're still in the special case where the order of our group is the power of a single prime. Then we need to move on to the more general case. So we'll do that in the next lecture. Okay, see ya.